Okay, well, hello everyone, and welcome to Special Interest Group on Broadband OBS Data Analysis during our 2021 Marine Seismology Symposium. So this session today is going to provide an overview of common roadblocks to using broadband OBS data, including an introduction to common sources of noise that you might be unfamiliar with if you have primarily worked only with onshore seismic data. This is also going to include introducing the automated tilt and compliance removal package, or ATACR, which can help you analyze and remove tilt and compliance noise on OBS data. So the first part of this is going to be a brief lecture, and then we're going to break out into groups to run a tutorial session on the Matlab version of this code, which is going to be run by myself with Josh Russell helping out. As well as the Python version of this code, which is going to be run by Pascal Audet, who is going to be helped out by William Hawley and Stephen Mosher. So before we get started, I just want to provide a brief overview of this package and some of the techniques that we're going to be using today. This package, the ATACR package, right now, this is the appropriate citation for it, but I want to emphasize that this is not really using any sort of new techniques. These tilt and compliance removal techniques are tried and true and have been around for a very long time, and are particularly using the approaches from Crawford and Webb in 2000, and Bell et al. In 2014, these two papers. So if you are interested in more of the details behind these techniques, I would highly recommend going to these sources. The ATACR code is an implementation of these techniques, and it also uses a set of quality control metrics to help assist providing accurate transfer function calculation. I also want to mention too, Zach Alon, who is not running any part of this tutorial, but he did a lot in terms of helping with the quality control aspects of this package. So I want to make sure that he's recognized for those efforts as well. So as I said, we're going to start off with an overview of how to use data from broadband OBSs, and this is going to last approximately 30 minutes. This is going to include a brief introduction of how to get started with using OBS data, common sources of noise to consider when evaluating the quality of your data, the overall concept of transfer functions and how we use them to remove noise and improve the quality of OBS data, and how this is implemented in the ATACR package, and an introduction to various methods to orient OBS instruments and how noise could influence the accuracy of such measurements. After that, we're going to switch over to the tutorial, and we're going to break out into two groups. Hopefully you all indicated your preference for group earlier in the Google survey that we sent out to everyone. And so we have a list of people who are going
Helen, I think we're kind of losing you a little bit.
Part of each respective breakout sec. We ask that for the first hour. Oh no, am I?
I think you're back now. Sorry, I'm sure you'll come back.
Hopefully this stays okay.
I think the last thing I heard was you saying if people had preferences on the room choice in the survey. So if that helps. Oh dear. Okay. Well, hopefully Helen will come back to us soon. I know that she's had a few connectivity issues here. Oh, okay. There you are. Would it help if I shared your slides, Helen? I see you now. But you're muted. Sorry.
Can you hear me?
Yes, I can.
Okay. I mean, yeah, why don't, if you can share my slides that would probably help.
Okay, yeah, let me just get that up and then we will start at that slide and we can go from there. Let's see. Sorry, everyone. We'll just, oh, can I? Keynote, I see. Sorry, just a second. And
I could also just try again. I think I'm now not on my Wi-Fi and on my wired connection, so it should hopefully be better.
Okay. Yeah, if you want to go ahead and try.
Yeah,
and then just start from the point when you said if people on the surveys indicated their preference, and we can place people in rooms as they need then. So
yeah. So yes, we'll be dividing into breakout rooms based on what your response was to the survey. And as Casey said, if there's any confusions or miscommunications, we will work to figure out how to get you into the appropriate breakout room. So for the first 60 minutes of the tutorial, that's going to be a step-by-step guide to the ATACR package. And so we ask that for those first 60 minutes of the tutorial, if you have any very specific questions, to kind of hold off until later. The last 30 minutes of the session in the 2 breakout rooms are scheduled for more detailed Q&A. So if you have specific questions about any issues or suggestions you have while running the code prior, or specific questions about your data set, please hold off until the last 30 minutes to ask those types of questions. I also will just put in a quick shameless plug for a talk I'm giving next week during the Harnessing Frontier Technology session. 10+ years of ocean bottom seismometer noise, fresh insights, and persistent questions. Again, we're going to go over just a introduction to the typical sources of noise on OBN instruments today, but this will have a more detailed discussion of some of the systematic causes of variation in these types of noise. So tune into that talk if you're more interested. But let's talk about how we get started with using broadband OBS data. To get the most out of broadband OBS seismic data, you generally must follow a somewhat different set of processing steps than you would for onshore data. To start off, you would start much the same way as you might for any seismic data set, answering the following questions for the analysis that you want to perform. What component of my seismic data do I want to use, and what frequency bands am I going to use for the analysis? Once you answer these questions, you then might ask a reasonable question: how noisy are the data? How usable is your data set going to be for your analysis? Up to here, this is pretty much the same as what you would be potentially doing for using an onshore seismic data set. But at this point, the processing will start to diverge for onshore and OBS data sets. First of all, there's an immediate distinction between using the vertical and horizontal components of these seismic instruments. If you're using the vertical components, you then need to decide if you should remove tilt or compliance noise before your analysis. The decision on whether or not you're going to perform this step will depend on what frequency bands you are working in, or relatedly, what type of analysis you are planning to perform with the data and the noise level of the initial data set. If you're using the horizontal components, you will need to estimate the orientation of your OBS because these instruments do not get oriented when they're deployed typically. And there's a variety of different types of methods that you can use to do this. These different methods in different frequency bands. So since noise levels can be frequency dependent for OBS data sets, your choice of orientation method may also wind up depending on the noise characteristics of your data set. So some of these aspects are a little bit intertwined, and we're going to touch on that today. So again, to aid in removing tilt and compliance noise from your OBS data set, you can use which uses transfer function techniques following Crawford and Webb and Bell et al. In conjunction with an automated quality control system to remove this noise from OBS instruments. And again, for horizontal orientations, which detail in the session today, but we'll present a few recent techniques for your reference. So first, introduction to the noise levels that can be expected for OBS data. Seismic data from OBS are comparatively noisy, particularly on the horizontal components. Chases routinely exceed the high noise model from Peterson et al. As shown by this compiled data set of noise spectra from a variety of OBS instruments. However, if you're just starting here, this should not be the point at which you stop your analysis because some of this noise can be removed. Tilt and compliance are two sources of noise that can be removed, and in a couple of slides we'll get into an introduction of what these noise sources actually are. They can be removed on the vertical data, and it can significantly improve the quality of your OBS data depending on the frequency band and the water depth of the instrument. For example, shown here is two seismic traces. These are the same exact data. In the same exact frequency bands from the same exact instrument. The gray one is the original data, and the black one is after tilt and compliance removal. And you can very clearly see that in the original, there's no obvious sign of any earthquake present in this data, whereas after tilt and compliance removal, we can very clearly see an earthquake arrival. So this step is really essential for getting the most out of your data set if you are working with vertical component data in a frequency band that is affected by these noise sources. And then lastly, if you're using the horizontal components, the orientation of the instrument must be calculated. Unlike land deployments, broadband OBSs are typically dropped off of a ship and sink to the seafloor. Therefore, the orientation of that instrument on the seafloor will be random and has to be calculated after instrument recovery. Okay, to make sure everyone is on the same page, I'll spend a few moments introducing some terminology we'll be using throughout this session, and that is used in the ATACR package. So first of all, we'll be talking a lot about looking at data in the frequency domain, meaning we've taken our normal seismic time series and converted it through a fast Fourier transform. This should be familiar to a lot of people, but if it's not, you definitely want to spend a little bit more time parsing out how we think about data in the spectral domain as opposed to the time domain. There's going to be 4 terms that we'll be using during the presentation today and in the ATACR tutorial that might not be familiar to you if you haven't done much work with the spectra of seismic data. The first and the most familiar probably to most of you are the autospectra, power spectra. And this is basically this shows the power levels of the seismometer at a range of frequencies. So how strong is the noise on your seismic instrument in a certain component at a particular frequency level. And so this is useful for assessing the noise level of instruments. And I should mention too, these would exist for all 4 components of an OBS instrument. And it's important to point out at this stage that a broadband OBS typically has 4 components of data, vertical, your 2 horizontal seismic components, and is also a pressure gauge that is deployed with the OBS. So you have a pressure component as well. The second of these terms is something called the admittance. And this and the following 2 are terms that represent the relationships between 2 different channels on an OBS instrument. So the admittance is essentially something that tells you about the amplitude of the transfer function between two components on an instrument. The transfer function is basically a way that we can predict expected data of one component from another component. And the admittance is basically a value that gives you an estimate of the gain of that transfer between those two components. The second one of these is coherence. And coherence, in my opinion, is actually one of the most useful ones to look at. And this basically answers the question, for a given frequency, how much of component X could you predict from component Y? So if you have a trace from your seismic or pressure data, how much of the component of your vertical seismometer channel could you predict just from knowing data on your pressure channel? And so coherence is shown on a scale from 0 to 1, where 1 indicates signals are highly coherent, and 0 indicates the signals are incoherent. And essentially, a transfer function technique will only wind up being useful for noise removal at frequencies where you have high coherence between two components. And then lastly, we have the phase, and this is, of course, just going to between two components of interest. And this is only going to really be meaningful for frequency two components. You wouldn't expect to have any sort of phase relationship between them. However, when you have high coherence between components, you would expect to have a phase relationship between them. Okay, so when you are preparing to use broadband OBS noise profiles of your instruments to decide what frequencies are going to be most appropriate for analysis and if you should remove tilt and compliance noise. There's really three main sources of noise that can affect how these power spectra look: microseism noise, compliance noise, and tilt noise. And we're going to go through the three of these in more detail. The simplest one of these, and the one that is probably most familiar to anyone who's only worked with land data, is of course the microseism noise, where we have the primary microseism at about 16 seconds and secondary microseism at about 8 seconds. For most OBS data sets, the secondary microseism is going to be higher than the primary microseism. And so what you can see here is noise power spectra for vertical, horizontal 1, and horizontal 2 components for, again, a variety of OBS instruments. And the secondary microseism bump you can very clearly see on most of the OBS instruments on the vertical and horizontal channels. You should notice that the primary microseism, you see an extra bump for a subset of instruments, but it's not necessarily really clear on all of the different instruments. I should mention that these power spectra are color-coded according to water depth. So when it comes to considering microseism noise, one of the main things you need to pay attention to is whether or not you're dealing with deep water instruments or shallow water instruments, because there's a significant difference between the relative strength of the primary microseism and the secondary microseism for shallow water instruments. Shown here are now power spectra for all instruments deployed in less than 500 meters of water, and they all have this much stronger primary microseism noise level compared to the secondary microseism noise level. However, again, to throw another wrench into the system, this so far really only seems seems to be true for shallow water shelf instruments deployed in the oceans. We have a couple of shallow water instruments that were deployed in Lake Malawi, and that is, those instruments have a different type of noise profile. So again, it's not necessarily a very clear-cut relationship all the time, and it's worth evaluating what the levels of these different microseism sources is for your particular data set. Okay, the second major source of noise to consider is compliance noise. And what compliance noise is, it is the displacement measured on the vertical component of the seismogram due to the loading of the water column from infragravity waves. So that's shown here in this cartoon from Crawford et al., where as you have the thickness of the water column varying above your seismometer, you will actually have a certain amount of depression of the seafloor that registers as a signal on your vertical component. So one of the telltale ways you can identify a strong source of compliance noise on your instrument is by looking at the coherence between your vertical and pressure components. So again, this is something where the amount of water above your instrument is changing in a way that is related to the up and down motion on your seismogram. So we would expect to have high coherence between the pressure gauge component and the vertical seismic component in a frequency where this noise is present. This is an example shown for two different instruments, and the frequency range where we have high compliance noise is highlighted in green. And compliance noise is kind of nice because there's actually a relationship between the frequency range at which compliance noise exists and the water depth of your instrument. So if you know the water depth of your OBS, you can predict at what frequencies you would expect your OBS instrument to be affected by compliance noise. And that relationship is shown here by this equation. And in general, compliance noise will extend to higher frequencies for instruments that are in shallower water compared to instruments that are deployed in deeper water. And this is borne out by the data. So here I'm showing an example of coherence profiles between the vertical and the pressure components for a variety of different OBS instruments deployed at many, many, many different water depths. This is basically, if you just imagine taking one of these coherence profiles and kind of turning it on its side, and now we're plotting them for many, many different instruments where black colors indicate high coherence between the pressure and the vertical channel, whereas white colors indicate low coherence between the pressure and the vertical channel. And if we then plot over that the predicted frequency range where we would expect there to be high coherence noise, we see a good agreement with our actual OBS data. So again, in general, we do see this higher coherence between the vertical and the pressure channels within the frequency range where we would expect to see high compliance noise for a given water depth of the instrument. The main takeaway from this is that if you are planning on using vertical OBS data within the frequency band that is highlighted in red here on this plot, you should probably plan to remove the compliance noise from that data if you want to get the most that you can out of your data set. And the last main source of noise on OBS instruments is tilt noise. The most regular source of tilt noise is bottom currents acting on a seismometer whose vertical axis is slightly tilted. And similar to the compliance noise, tilt noise is often most easily identified by looking at coherence again, but this time between the vertical and horizontal channels rather than the vertical and the pressure channel. In this kind of framework of thinking about tilt noise, it's typically very unidirectional. So for example, here I'm showing the coherence between the vertical and the horizontal one channel, and we can see over a wide frequency range, there is high coherence for this particular instrument. And this would basically be implying that there's a high source of tilt noise, and it is primarily in the horizontal one direction. But it could be in any sort of direction between your horizontal components. If tilt noise is present, it typically dominates your signal. So here we have an example of an instrument that has high tilt noise, again, mostly in the horizontal one direction, as shown by this coherence plot. And what you should notice is that there's high coherence in the vertical with the horizontal one, low coherence between vertical and horizontal two, again, because most of the tilt noise is in the H1 direction, but also low tilt noise between, low coherence between the vertical and pressure channel. And so just because we have low coherence between the vertical and pressure channel at this stage of analysis does not necessarily mean that compliance noise is not also present. It's just at this point, the tilt noise is dominating the signal. And so that is going to be what you're going to see the most evidence of when you're looking at the coherence of these, of this data set. And Sam Bell nicely points this out in his paper, where he shows coherence between the vertical and pressure channel prior to tilt noise removal, shown in the top plot here, and then after tilt noise removal, shown in this middle plot. And what you should notice is that the coherence between the vertical and the pressure increases after the tilt noise has been removed from the vertical. So once we remove that tilt noise from the vertical, then we can see high coherence indicating the presence of compliance noise, and then that can also be removed to further clean up our vertical channel. And this is just a quick plot showing the same type of signal that I showed between the coherence and the vertical and the pressure for sampling of OBS instruments. But now we're showing it for the vertical and horizontal one and vertical and horizontal two channels. And what you should notice is that there's not as systematic of any sort of relationship between water depth and tilt as what we see for the compliance noise. And in fact, Bell et al. Suggested tilt noise is typically more dependent on the instrument design rather than water depth or any of these other factors. So there's some variation again in the sources of tilt versus compliance noise and the variables that affect tilt and compliance noise. But the good news is that tilt and compliance noise can be removed from your vertical channel of seismometer data through the use of transfer functions. And so you can calculate a transfer function for your vertical and horizontal channels, and you can calculate transfer function between your vertical and pressure channels to remove the portion of data that is caused by the coherent noise between these two different channels. So again, depending on the water depth of your instrument and the frequency of interest, this can yield perhaps a minor improvement to a very, very significant improvement. And again, I'm showing here a comparison of original versus tilt and corrected data for two different OBS instruments. The one on the left is a shallow water instrument. The one on the right is a deep water instrument, both of which have improved signal to noise ratios after tilt and compliance correction. You can see that the effect is much more obvious at the shallow water instrument. And so this technique is very useful, and how useful it is will depend on the particular properties of the instrument you're using. So this again is a very brief introduction, and if these terms are things that you've never heard before, I highly encourage you to read some of the papers that I referenced at the beginning, and again you can also look at the manual for the ATACR package for more detail on all of this. It's a lot to take in if you've never heard of any of these noise sources or concepts before. But the good news is that the ATACR package implements these tried and true tilt and compliance noise removal techniques, but also includes quality control steps to aid in the analysis and correction of these data sets. So hopefully this will lower or help to lower a bit of the barrier to entry of really being able to assess the noise, the quality of your data, and to robustly correct seismic components before the analysis that you might want to do with an OBS data set. This is a flow chart for this.
Oh, sorry, Helen. I think we're losing you again.
That are implemented in the available in the manual for that code. Am I back?
And you're back.
Back. Okay. Where did I cut out?
Oh man, what was it? It was just the end. It sounded like you were kind of wrapping up the slide. Josh, did you quite catch it?
I think you had just said this is a flowchart showing, and then you basically cut out.
Okay.
Great. Okay. Anyway, this is a flowchart that shows the steps that are implemented in the ATACR package. So if you are more interested in it, this is available in the manual for the Matlab version of the code. And just briefly, I'll show a few examples of some of the plots that are spit out by this code, but we'll have time to go over this in more detail during the actual tutorial session. So again, to calculate an accurate transfer function to do these corrections, we want to have data that is representative of the background noise at a particular station. And so what the ATACR package does is it implements quality control that identifies and removes any segments of data that increase the overall variance of a noise data set above a user specified tolerance value to avoid any earthquakes or other transient signals accidentally being incorporated into the calculation of the transfer functions. So the first stage of this is implemented when we calculate daily noise spectra for the instruments. And an example of this is shown here. This is a spectrogram showing a day of data from an OBS instrument for our 3 seismometer and pressure channels. And what you can see here is the 2 segments on the pressure channel that look anomalous have been flagged by this code and have been removed from the calculation of the spectra. And so overall, the transfer function should reflect site properties of a particular OBS instrument that includes the properties of the sediment and seafloor on which the OBS is resting, as well as the individual instrument. And it shouldn't vary necessarily over the course of a deployment. However, there is some evidence that in some cases, some of these properties do actually vary over the course of a deployment. And so another piece of this is assessing whether or not it's appropriate to use a transfer function that is calculated over an average of data over the entire deployment, or if it might be more appropriate to calculate transfer functions using a subset of the data closer to an earthquake of interest that you want to correct your data for. And so this is an example of, again, from Bell et al., showing variation in tilt direction and amount over the course of a deployment for two different instances. Tilt direction is varying, horizontal components will be varying slightly over the deployment as well. So this might be an example where a more subset of daily averaged transfer functions might be more appropriate for that data set. And the ATACR quality control procedure is implemented at the daily level such that you can accurately calculate transfer functions for only a day or so of data if you want. And again, this is not exclusive to the Cascade Initiative experiment. We've seen this at other experiments as well. This is an example of a station from the Plume deployment. And again, what you should notice here is that there is a slight variation in the orientation of maximum tilt direction over the course of a deployment. So this definitely does affect some instruments sometimes. And so lastly, the point of all of this is that you can produce a corrected seismogram, and this is a final set of figures that the ATACR package will produce once you have calculated robust transfer functions and have applied them to your data set. And so again, this is going from uncorrected vertical data to a really nice, much nicer looking corrected seismogram on the bottom. And so this is shown in periods where we might typically be looking for Rayleigh waves from earthquakes, and that is definitely a very traditional method of applying these tilts and compliance techniques. I do just very briefly, and I know I'm a little bit over because of the internet issues, but I want to just briefly mention that there's still a lot of stuff we don't fully know about what is always the best way to apply these corrections. And so more and more published papers showing comparisons of actions have been applied. And so for example, from Tan and Ritzwaller up top, we're showing a comparison of the raw data from the Cascadia Initiative at 20 to 30 seconds versus, but interestingly, people have been starting to apply some of these transfer function techniques in more novel period bands. For example, Bowden et al. Showed that if you use this transfer function technique at microseism periods in your ambient noise cross correlations, you can wind up reducing the amplitude of your fundamental mode and increasing the amplitude of first overtone observations. And so this is a figure from Josh Russell showing a similar result, and a comparison of trying to apply that same type of correction in the microseism band at two different deployments, Young Orca in open ocean deep water versus ENAM, which is located at the coastline of the Eastern North American margin. And this is the same exact technique. Blue is showing the original data, black is showing the data after the correction. And what you should take away from this is that for the Young Orca data set, again, we're seeing that similar observation of reduction of fundamental mode and amplification of first overtone post-correction, but now we don't see any evidence of that. So again, I just want to re-emphasize that there are still questions about, how we can actually get the most out of this data, depending on what type of analysis you want to do. So it is definitely open to exploration and suggestions from members of the community for how we can continue to improve these techniques. And again, I'm just going to really briefly wrap up with the horizontal orientations. As I said at the beginning, this is not the main portion of the tutorial today, but there's a variety of different techniques out there that can be used to estimate horizontal orientations of your OBS instruments, several of which I've highlighted here and have given some citations for reference. Using surface waves, ambient noise, body waves, receiver function, active sources, ship noise. And all of these can be useful. I just want to end, though, on the fact that all of these different orientation methods operate in different frequency bands. And again, the noise character of our OBS instruments is going to be frequency dependent. Particularly with regard to a particular depth OBS instrument. And so, for example, Dorn and Lasky showed comparisons of the orientation uncertainty using this orientation method based on surface waves for a variety of different OBS instruments at a variety of different water depths. And the white colored dots have higher uncertainty. The black colored dots have lower uncertainty. And what you might notice is that there's a large amount of shallow water instruments that have relatively high uncertainty, higher uncertainty compared to the deeper water instruments. And this isn't necessarily that surprising, because if we go back to thinking about what frequency bands our compliance noise operates in for a particular water depth of instrument, as we get to shallower and shallow water, we're going to have higher and higher compliance noise in the frequency band that we would normally analyze surface waves in. And so again, this is just a brief demonstration of, potentially one of the ways that it's important to think about your sources of noise when choosing your orientation method and how exactly you're going to filter your data. So this is, expected. So this is potentially one reason that might be contributing to this trend that we're seeing between shallow water instruments and deeper water instruments. So with that, I apologize again for my, oops. Sorry, I did not mean to stop sharing, but I apologize for my internet. And I know that was a lot crammed in to a short period of time, particularly if these are all terms that you have never heard of before. But that is why we have the next hour and a half for the tutorial and questions. And so I would also highly encourage anyone to email me or other OBS expert users that are at this meeting if they have specific questions about any of these terms and don't know where to get started. So with that, I will open it up.
Thanks so much, Helen, and great job rolling with that. I know Hawaii is a bit of a rough place to get a good internet signal there, so you're doing great.
Okay, so let's see.
There was a question from Stephen Hicks I can read aloud to you. Presumably with tilt and compliance corrections, you lose information about absolute ground motion amplitudes. For example, waveform modeling.
There's definitely concern about this, and I think if anyone else is in the room who knows more about this, please feel free to jump in. But yeah, Bell et al. Definitely go into this a little bit, but I'm not sure at what level of accuracy it becomes a really serious issue, to be honest. It's definitely a concern about whether or not you're, just removing the water-driven source of the noise versus some sort of seismic related component of the noise. But yeah, I would say that it's falls a little bit more into one of those areas that people are still investigating and working with. But does anyone else want to jump in more on this?
Yeah, this is Wayne Crawford. Can you hear me? Yeah, I would just say that in general with compliance and the tilt, the transfer functions are the inputs are not ground motion. Well, and so to me, if you're not really distorting very far the ground motion signal, if you're working in the Rayleigh waves with the microseisms, you could have something because you're going from a ground motion to a ground motion, so you're going to be getting rid of some ground motion. But the currents and the ocean waves are another source of signal. So you're just sort of, if you're doing it right, you're just moving those signals there, and you're not taking too much away. You could worry about the fact that when you're taking away the horizontal, you'll be getting rid of some of the seismic signal that's in the horizontal too. But if you look at the transfer functions, they're so much smaller than the transfer function between ground motion and ground motion that it's a distortion on the order of 1% or 2%.
I would also jump in and say that's one of the best reasons to use these sort of long-term averages in some way for the compliance corrections, because then you're not getting the necessarily like the spurious random corrections that you're adding to it. If you're using the longer term averages, that should help out a lot with just ensuring the compliance correction is the compliance signal and not something else.
And then maybe we'll just do this last one from Emily Rowland really quick and then move on, if that sounds good. Are there examples of tilt noise in the frequency range above the microseism peak appropriate for short period instruments?
Yeah, so not to my knowledge. Let me kind of just, hold on. Let me just share my screen again really quickly. Wait, 1 second.
No worries, and I'll just say while you bring that up that there were some other comments made about the OBSIC tech mailing list and also what's OBSIC is doing for horizontals and other pre-processing for sort of lowering this barrier to using that data. So make sure to sign up for that mailing list and check that out.
Yeah, so whoops, I don't know why that's so big. Yeah, so again, just to kind of point this out again, because this is really kind of a, measure of where you have some coherent signal between any of these components. So roughly, your secondary microseism is going to be somewhere kind of around in this range, if you can see my cursor.
Yeah, we got it.
But so, okay. But yeah, so when you look at the tilt noise, or the places where you have high coherence between the vertical and the horizontal components, what you'll notice is, one, that there isn't this kind of, systematic depth dependence like there was for the compliance noise. And where you do have high coherence, it kind of ends, right at about 10-ish seconds, or kind of where you start to get into the secondary microseism. And there isn't really any obvious high coherence, or at least as strong high coherence between bands. Now, granted, too, the plots that I'm showing here only go up to 1 second. So that's thinking about for short period instruments.
Okay, a little bit in and out there, but I think I got the gist of it. So thank you for that.
But I also see that,
oh,
and
sorry.
also, so Wayne Crawford also has put a, looks like something, reference in the chat.
Okay, we got like the end of it there. Sorry, it sounds like you're caught back up with us again. So Helen, as you come back to where we're at in reality time-wise, if you want to go ahead, I don't know if there's anything you can do for switching internets or trying the other one, feel free to, but it is now a good time to switch to breakouts.
Yeah, I think it is. If no one else has any, there are a couple of other questions, although I think in the chat. Joe Burns asked, does the order of operations matter? Should you remove tilt noise before calculating coherence between Z and P? There's definitely some papers recently that have looked at those. I think the argument, as I understand it, is that so your transfer function will be more accurately resolved for the noise source that is larger amplitude. And so it makes sense to go in the order of which noise source has the higher coherence, because that's going to give you a more accurate transfer function. There are some papers recently that have started exploring looking at different orders of removing this noise, and also even sometimes I think sequential removing, like, so for example, maybe compliance and then tilt and then compliance again. And I can kind of try to find some of those references and send them to you if you're interested. But I will say a lot of this, for most data sets, for just a improvement in noise level, the tried and true kind of like remove your tilt, remove your compliance, remove your tilt if you have it, and remove your compliance does a really good job for just getting that first order of improvement on the data set. So a lot of these more detailed questions are much more in the weeds with trying to really get the most out of your data set.
Okay, in the interest of time, should we okay.
Yeah, yes, me too.
Okay, yeah, but thank you so much for that overview. I mean, those are amazing improvements, being able to see those signals through all of that. So very important processes. So now we'll go ahead. So if you registered in advance for this, you indicated a preference of programming languages. So we're going to now divide and send you off into 2 different breakout sessions. Room 1 will be with Pascal in the Python session, and room 2 will be Helen in the Matlab session. And if you did not register or you are not on our list for some reason, we can assign you a breakout session of your choice. But so just sit tight in the main session, and Kristen and I will work with you on that. If you have any questions or issues that come up, just direct message either Kristen or me, Casey. Sound good? Everyone's ready to be sent off? From organizers, sorry, I'm looking at you guys. Great. Okay, Kristen, want to go ahead and send them off? All right, so just click that link and we will see you later.
Looks like people are back.
Yeah, I am beat. Non-stop talking.
That's a lot. You guys are doing great.
Were there any other general question that came up that might be worth repeating, or?
I don't think there was anything really in the MATLAB session. Josh, did you think, was there anything about a general question that would be worth repeating?
How to coordinate. The packaging will change, and the reason for that is because they're open source codes and people can contribute, and therefore there might be 2 communities contributing to the code in different ways, and therefore they might diverge at some point, but most likely this will be through some added products that you can do with the code more than the core routines, which should remain consistent. So that will be up to us you and I, Helen, to look into this. But the more people contribute, I think the more stable these codes will become. And so that's why I encourage everybody to raise issues, fork the repositories, and propose changes if they'd like, and maybe fix bugs if they find any, which is always great. Yeah.
Yeah. Were there any other questions just from the general audience who's still here? Okay, I see one in the chat. We're on MCS data, not seismology. Can I ask the seismic data from OBS is a record earthquakes? Yeah, so for the most part, the traditional way these corrections are applied are for kind of the frequency bands that we would be looking at for teleseismic earthquake data. Again, though, as we deploy OBS in more kind of unique environments, deploy them in more shallow water, the frequencies at which these noise sources exist change, as well as more people starting to apply these transfer techniques and transfer function techniques in unique ways in the microseism band and potentially other coherent bands as they continue to investigate this data. So I think there's still a lot of areas for open investigation of applying these types of techniques in non-traditional ways and non-traditional frequency bands. But it's definitely rooted more in typical OBS earthquake data and analyses that would use that type of data for applying these corrections. Okay, if there are any other questions, I mean, Pascal and I are always happy to email with people, or you can message us on the Pathables website for the meeting and get in touch that way. But if not, I think then we can end the session at this point, right? Okay, well, thanks everyone again for attending.
Thank you.
Great job.
Thank you so much. That was awesome. Yeah, I really enjoy it. So thank you.
Thank you.
Yeah, we'll just leave it open for a little bit just for you to see all the praise.
I maybe have like a little specialized question, like Martin from Ocean Networks Canada. Like I was like wondering, is it like possible to kind of like figure out like corrections and then apply them to a data stream, or is it well, I guess like it's probably nothing that you ever would have done before, but you have like, for example, like these earthquake early warning sensors on the seafloor that also have like pressure built in, and is it maybe possible to kind of like with like a streaming data set, like on the go, compute like the compliance correction and maybe apply it, or you're also sending data to Iris that's like, live in real time. And then, maybe would it be possible to have like virtual sensors, going to Iris so that people don't need to run the code, but, maybe there's like already a pre-processed version at Iris, like kind of like a rough cut.
Yeah, if you don't mind, I can take the stab at answering this. This is an excellent question, and John Collins raised this yesterday during the forgot the name of the panel, but anyways, he mentioned that there will be these noise corrected components on Iris now. Someone is working on uploading those for several experiments, but these are done after the fact. It is certainly, I can envision that this could be applied in real time, because all you need to do is save maybe a week of data as you go. And these are applied, they're like lightning fast to calculate. And therefore it's really easy to do on the fly in an early warning framework, I would say. So this is certainly possible. Probably need to tweak the code a little bit, but other than that, this should be feasible. In terms of uploading these corrections to Iris, for example, I think it's a great resource, but it should also come with a caveat that there have been choices made when producing these corrected data, and it needs to be clearly documented what those are. And hopefully, well, I don't know if any of these codes are going to become the standard for doing these things, but at least reproduce like openly how these were created using these codes, and therefore the users can have an idea of how reliable they are and what options were used in setting those up. But there's still value in putting those up for everybody to download from Iris. Helen, did you want to add anything else?
No, I mean, it's pretty much, yeah, I think that sums it up pretty well. Yeah, I mean, I think the principle of it is you would just need enough of a lead-in of data set in order to calculate an accurate transfer function. But in principle, once you have that, you could then repeatedly apply it to data as it comes in terms of, thinking about if it was real time, what's the proper way you're going to window and kind of cut that data, and how quickly it would be able to be implemented for, say, something like earthquake early warning would all be things you'd have to think through, but I would imagine that all be possible. But again, just to echo to what Pascal said, this is very important that if these products do become available, that we know at what point kind of the standard parameters that we are using for calculating these transfer functions, for what uses that's appropriate, and for what uses the user might want to have thought about changing some of these parameters, and making sure all that's well documented so that everyone can make their own decisions about how to use potentially these data products or to reprocess them themselves is going to be important for the community.
Yeah, thank you.
All right, let's call it for tonight. Thank you so much, everybody. Take care. And yeah, well done. Well done, organizers, you guys.
Yeah. Thanks, guys, Josh, Stephen, and William.
Yeah.
Appreciate it.
Yeah, thanks.